Okay, so this is the next session in the course on artificial intelligence. So we spoke about different types of search up to this point in time. So we first of all spoke about the uninformed search and then the informed search and the game playing search. So here basically we start from an initial starting position and move to the goal state, going from one state to another state till we reach the goal state. So what we needed to define there was we had to define what is a state, what is the initial state, what is the goal state, and what are the operators or actions which take you from one state to another state. So what we haven't covered is something like local search, where you move from one point in the solution space to another point in the solution space uh, by seeing which is the best direction to move depending on the evaluation. So you just keep moving till you reach the best position. So here actually the steps that have been taken to reach that goal state is not important. It's just that we need to reach the goal state. We need to know which is the goal state. So that's the basic idea in this local search. So here the path to the goal does not matter. Okay, so generally what is done is, in the solution space you have one node which is known as the current node, which could be any point taken at random, and you move from there to neighboring states. So what do you mean by neighboring states? So we can look at a neighboring state as a state which is the closest or the closer points to this point. So when we say neighboring, it could be like suppose you have say the xy coordinate of a point. Maybe you could move the x and y coordinate or one of them by some epsilon. So if you move by some epsilon, some small distance, then we can call that a neighbor. Another way to find neighbors is, for example, if the present node consists of a vector, then we could change say one value in that vector by some small amount, or if it is zeros and ones, you could change one position or two positions. If it's 0, you can make it 1, if it's 1, you can make it 0, etc. So these are all different ways of finding neighbors of the any particular point. We do not maintain any path of how you reach there from your current state. So what are the advantages over here? So we can see the advantages is that it uses very little memory, because we are just maintaining one current state and the solution space, and finds reasonable solutions in large or infinite search spaces. So this is the advantages of this local search algorithms. So if you look at problems like optimization, where we say we need to find maximum of an objective function or a minimum of an objective function, so there what you have is something like a state space in which you need to move to the best position, okay, along the function that you have. And these type of optimization problems will not fit into the type of search algorithms we have already covered. So suppose you consider a solution space in this way. So you can see here that the y-axis here gives the objective function of the points. Okay, so and you have the location or the points along the y-axis over here. So this y-axis is this is the state space that we have, okay, and the points along this curve are points in the solution space. So now we need to search this curve over here to find, say, the global maximum. Okay. So how do we go about doing that? So suppose you take some current point. So suppose this is your current point. You move along the function in a direction where the objective function increases, and you keep doing that. Okay, so once you move to a point which has a better objective function than the present point, from there again you look at the neighbors and you find a point which has a better objective function, and you keep doing that till you reach the maximum. So what we have here, since we are talking about objective function, we talk about the global maximum. We want the maximum. If it was a cost function, then obviously we would have wanted the minimum or the global minimum. So we need to actually explore this landscape which is given over here to find the point that we are basically looking for. So an optimal algorithm is one which finds the global maximum or the global minimum and does not get stuck in some other point and talk about that point as the global maximum or the minimum that we are basically looking for. Okay, so one such algorithm is the hill climbing algorithm. So what is the hill climbing algorithm? It moves in the direction of the steepest ascent, okay, and it keeps continuously moving in the direction of the increasing value, and when it reaches a point where there are no more increasing values, okay, so suppose all the points around that has only a decreasing value or a value which is less than that particular point, then we say that is a peak that we have looked for, okay. And it only looks at the neighbors of the current node. It does not look anywhere else. Okay, so it keeps moving in that direction. So it is known as a greedy local search because at that particular point in time you try to choose the neighboring state without looking somewhere ahead. Okay, at that point this is the best way to go. So that's what you talk about as the greedy algorithm, and the greedy algorithm will work well and move towards the solution, but there are some drawbacks, so we need to see what these drawbacks basically are. Okay. So why is it that the hill climbing gets stuck? So there may be, first of all, what is called as the local maximum. So what happens is when you come to a peak which is a local maximum, then all the neighboring nodes of that particular current node will have an objective value which is less than this particular node. So because of that, it's not able to move beyond that node, and the local maximum will be given as the final solution, but it's not really the final solution. So that is one problem. Another is when you get a ridge. Okay, so when you get a ridge, what happens? You get a number of points which have the same objective function, and you find that all the points on either sides of the ridge will have objective functions which are less than this. So it falls down. Okay, so that also will create a problem. So, and the third one is a plateau. So when you have a flat area, okay, in that flat area you don't make any progress because all the points will have the same objective function. So if we look at this figure over here, we can say that this is your local minima, local maxima, sorry. So if this is your global maximum, and if you are moving from this point, you will get stuck at this local maximum, and it will give this local maximum as the global maximum. And then when you come to some place like this, this is a flat region, okay, or a plateau. So in the plateau you find that the objective function value doesn't change much, right? Here again you have another flat region. So in these regions you may have problems. Now if we look at this this is what we call a ridge. Okay, so you have the points here where all these points have the same objective function, and all the points on either sides of this will be having the objective function which is lower than these. Okay, so what will happen is this will be like a local maxima, and it will be stuck in the local maxima in whichever direction it goes. So this is another problem which we have. So we can see that these three problems will be there, and if we look at this figure, okay, this figure will give you your the algorithm for hill climbing. So what is it that you do? You take some current node, okay. So once you take a current node, you find a neighbor, and if the neighbor value is less than this current value, okay, then you return the current state, otherwise you move to the neighboring state. So this is the problem which uh, we are working on over here. Okay. Okay, so there are some variations to this problem which are used to get better solutions. The first one is what is called the stochastic hill climbing. So what you do here is that you choose, suppose there are a number of moves that are possible to go in the towards the uphill moves, okay. And the probability of these moves will vary depending on the steepness. So the steeper it is, the better will be the probability of moving to that point. So you choose according to probability, you try to move to the neighboring points. Okay, so here this converges more slowly than steepest descent, because you are considering number of points together, not just one point. And it is found that in some cases it gives better results. Next is what is called the first choice hill climbing. Implement stochastic hill climbing by generating successors randomly until one is generated which is better than the current state. So as soon as you find one which gives a solution which is better than the current state, you move there. Okay, so that is called the first choice hill climbing. And next one is what is called the random restart hill climbing. So you are going to do hill climbing from a number of current positions, okay, not just one current positions. So for each position that you use, you will be getting one global minimum, and then you can put them all together and decide which is the local minimum, which is the global minimum. Okay. So if each hill climbing search has a probability P of success, okay, then the expected number of restarts required is 1 by P. So at least 1 by P points you have to take as current points at random, and you have to carry out random restart hill climbing. So what you find is that even if there are local maxima, if there are plateaus, there are ridges, in spite of all that, this will give you a better result. Obviously, it may take a little longer than using the other methods. Even if you have exponential number of local maxima, still it works reasonably well. Okay, so these are all variations of the hill climbing algorithm. So what I would like to now talk about is what are called the stochastic search techniques. So what happens in this stochastic search techniques is that if you want to solve a particular problem, you start with one point which could be a solution to this particular point, or it has the same format as your solution, and then from there you keep moving to some other points around, okay, and each string that is evaluated okay, will tell you how well that string solves the problem. Okay, so in other words, it is known as it's a evaluation function or the penalty function, and it's also called the fitness function. So how fit is that particular string in solving the problem that you are basically looking at. So there are a number of stochastic search techniques. So again, you may start with one current solution, or you can start with a number of current solutions. So from these current solutions, you have some operators. Okay, so you are going to evaluate the current solutions, and you are going to get the fitness function, and depending on that fitness function, you are going to get other neighboring solutions, okay, using these operators on these, and you are going to evaluate those, and you keep doing that, and whichever string gives you the best fitness value, that is the one which is finally chosen. So one popular technique here is what is called the genetic algorithm. So we'll look at the genetic algorithm first. So genetic algorithm is based on genetic recombination and survival of the fittest. So genetic recombination means if you have two strings, you are going to combine those two strings in some way to form two more strings. So you are combining them to get new strings basically. And survival of the fittest is like the once you evaluate the strings and you get the fitness function of those strings, the string which has a higher fitness has a higher probability of being chosen. So that is what we mean by survival of the fittest. And this genetic algorithm was actually proposed by John Holland, and somewhere around in the 1960s basically. And what you find is that it's a robust algorithm, okay, to evolve better organisms. And what you are going to do is you are going to evolve a number of organisms. So if you have a particular problem for which you want a solution, you don't start with just one candidate solution. They are known as the candidate solutions. You start with a population of candidate solutions, and you move from one population to the next population using a number of operators. So we will talk about what those operators are a little later. So the operators are such that if you take the population 2 as compared to the first population, the population which is generated from this population, you find that the evolved population will have better fitness than the original one. And then using that you can again do the same procedure a number of times. And after doing this a number of for a number of generations, maybe 50, 100, 500,000, whatever you want or whatever is good for your problem at hand, then you find the string which has the best fitness, and that will be the final solution which you are looking for. So it's very good for things like optimization algorithms here, because in the optimization algorithms you have something which you want to minimize or you want to maximize, right? So that is the fitness which you are looking at. So in what way does it differ from the standard methods? So we have a lot of standard methods of optimization. In what way does this differ from that? You work with an encoding of the parameters and not with the parameters themselves. Okay, that is one. Secondly, you work with a population of solutions or candidate solutions, and you use a payoff function or a fitness function to evaluate these solutions. And you use probabilistic transition rules rather than deterministic transition rules. So what do you mean by probabilistic transition rules? You are going to use some probabilistic values. So randomly you may be generating some probabilities, and depending on those probabilities you are moving forward in your algorithm. So this basically means that every time you run the algorithm, you will find that you are going to get different results, not exactly the same result. That's what we mean by probabilistic transition rules. Okay, so when you use a probabilistic transition, you find that you don't get the same strings every time you run your algorithm. Okay, so what are the benefits of GAs? It's easy to understand. We'll just go through it now. It's modular and it's separated from the application. So you're taking the application and you're finding out what is the candidate solution. Okay, so the candidate solution is an encoding of the parameters of your problem, and then you're using those in a modular fashion. So it is separated from the application as such. And it supports multi-objective optimization, good for noisy environments, which means it gives robust results basically. And you always get an answer. Okay, so this answer may not be the same every time, right? Every time you may find that you get a different answer, but you will get an answer, and the longer you run it, the better your answer is going to be. Okay. So you may get a satisfactory solution to your problem, okay, not necessarily the exact solution. And inherently parallel. So what you can do is, if you are having a population of say n strings, you can do all those n strings in parallel. So the evaluation of those n strings, getting the fitness values, etc., can be done in parallel. And when you do crossover, you are going to do 2 strings at a time, or some of the operators, when you do 2 strings at a time, you can again do it in parallel. So it's going to be a distributed algorithm, and therefore you can speed it up because it's parallelizable basically. And you can speed up and improve. You can use something about the knowledge of the problem domain that you have gained. Okay. And if you have got some previous or alternate solutions, you can exploit that to speed it up. So what you can do is, when you know some alternative solutions which exist, you can take those alternative solutions as your initial solution here. So what you will find is that because you have done that, you will get the solution faster, and also it may be more exact, it may give a better solution. And flexible building blocks for hybrid applications. So what you can do is that there are many applications where instead of using those algorithms, say, to find weights, for example, if you take a neural network, and in the neural network you need to find the weights in all the edges in the neural network, you can use the GA to find the weights of your neural network. Okay, what are the best weights that you can use? So in this way you can use hybrid methods. So you can also use methods for finding the set of features in a machine learning algorithm, and doing classification. All these tasks can be done using GAs, and it's been used for a lot of applications in a lot of fields. Okay, so the applications are there in almost every field that you can think of. Okay, you may not want to use the GA everywhere. Okay, so suppose you have a fairly straightforward optimization problem which is very easily solvable. There is no need to use GAs. Okay, when you find that any alternative ways of doing things are very slow or become complicated, for example, if you take say optimization, multi-objective optimization, you may find that using the classical optimization techniques may be a little difficult, or even to formulate the problem may be a little complicated. In such cases, using this genetic algorithms will help. And When you need an exploratory tool to examine new approaches, you could use that. And then when you want to hybridize, benefits of the GA technology when it meets your key problem requirements. So in all these cases you can use your GA. So it may not be necessary to use it in all cases. Okay, it may be much faster to use some other alternative techniques. Only in cases where it is required you can use your GA. So this gives you the algorithm of your the genetic algorithm. So what you are doing is you are generating an initial population P of n strings. So what is these n strings? Each string in the population is a candidate solution to the problem that you are looking for. For example, if suppose you are trying to say you want to okay, so you want to say maximize say x squared. Okay, so this is your optimization problem that you have. What you can do is you can represent your x over here by a binary string. Okay, for example, if you say you are using say digit 8, you can say 1000 will represent 8, right? And suppose you are saying you are representing 12, you can say 1100 represents 12, etc. Right? So you can have a string. For example, if you say that your x is going to vary between 0 and say 32, okay, you can have a 5-digit binary string. Okay, so suppose I have like this. So this will represent actually 24, okay, or if you have a 0 here, okay, that's the exactly what I have put there. So say 11010, okay, so this would be represented by say 13, so this is 13. So in this way you can represent it as a binary string, and representing as a binary string actually helps you to work on the operators which we are going to use over here. Okay, so what we do basically is generate the initial population of n strings. Another example I can give is, suppose you are trying to find in machine learning, you have an algorithm where you have say D features, okay, so F1, F2 up to Fd. You want to find a subset of features which gives a better result. So what you do is each of the each of these in the string represents one feature, and if it is 1, it means that feature exists. If it is 0, feature doesn't exist. Okay, so you could have a string like this which represents a subset of features which is being used. Okay, so I'll come to the evaluation. So you'll have initial population of n strings, and you have to fix n. N is the population, the size of your population, and probability of crossover and probability of mutation, which I will talk about. Those are the operators which we are using. I will talk about that. And iter gives you the number of iterations you want to run your algorithm for. It could be 100, it could be 500, it could be 1000. Okay, it depends on what you are working for. So first you evaluate the fitness of your population P. Okay, so you will have n strings and you can find the fitness of these strings. So for example, when you have maximize x squared, the fitness of the string will be, you can find x from the string and you can square it, right? And that would be the fitness of the string. Or if you have say a subset of features, you can use only that subset of features, and you can run the classification algorithm on your training data set, and you can see what is the classification accuracy that you are getting, and that classification accuracy could be the fitness of your string. So once you evaluate the fitness, then you generate P1 from P by using selection. So you have an operator called selection or reproduction, okay. So once you do that, you select P2 from P1 by doing crossover, which is another operator which you are using, and select P3 from P2 by using mutation. So once you do all these things, you get generation P3, okay, and so your generation P3 gives you your next generation. So set P is equal to P3 and K equals to K plus 1, and you go back to 2 and again evaluate the fitness, and you keep doing this till you have reached the number of iterations that you are working on. So once you reach the number of iterations, for example, suppose you have set iter to be equal to 500. Suppose 500 is over, you come out from here, and out of all the strings that you have generated up to this point in time, output the string with the best fitness generated so far, and that would be the solution that you want here. Obviously, in this particular problem which we are talking about, when we say maximize x squared and we are representing it by binary number like this, we can say that the best would be if all of them are 1. Obviously, when all of them are 1, you are going to get the maximum value. For example, you may get 32. And when you want to maximize x squared, x equal to with all these values of 1 gives you your best result. So this gives the algorithm for genetic algorithm. Now we will continue by talking about how do we do selection, crossover, mutation, and go further in the algorithm. So we'll stop at this point and we'll continue the rest of the genetic algorithm in the next session.